All right. So what'd you figure out? Did you figure this out? Is it cyclic or not? I see people shaking their heads back and forth. That's correct. It's not cyclic. None of these elements is a generator. Certainly one is the identity. And the order of one is 1. This is the group operation is multiplication mod 16, not addition. You can try to see if 3 is a generator. 3 squared is 9. 3 cubed is, of course, 27, but mod by 16, that gives 11. 3 to the 4th is 81, or we could think of it as 3 times 11 is 33. Mod 16 is 1. The order of 3 is 4. 5 squared is 25. Mod 16 is 9. 5 cubed, say, is 9 times 5 is 45. Mod 16 is what? 13. 5 to the 4th, 5 times 13 would be what, 65, is that right? 65, mod 16 is going to be 1. So the order of 5 is also 4. There are some elements of order 2. Certainly, actually, since 3 has order 4, 3 squared would have order 2. 9 would have order 2. 9 squared is 81. Divide 81 by 16, you get a remainder of 1. 9 has order 2. Also, well, 5 squared was 9 as well. Oops, 7 squared would be 49. Mod 16 is 1. 7 has order 2. Yeah, none of these elements end up having order 8. Okay. So if I gave you this on the test, certainly something that's doable within, maybe you might say 7 or 8 minutes. Is there anything I could do to help you go a little quicker? Maybe, not ruling it out, but just for the moment, just realize you should be able to do something similar on a test, like answer an open-ended question like that with reasons based on calculations, for example. By the way, somebody did ask, many of the problems that you've been turning in have been proofs. So what proportion of the test is proofs? And I did look up the exam I gave 3 years ago, and I saw the first exam about 25 to 30% of the exam was proofs as far as the points go. The rest of the exam consisted of definition statements, theorem statements, true, false, multiple choice, and calculation problems. Is the rest of the exam. I don't know about exams 2, 3, and the final exams at the moment, but that's what I saw in the first exam. Mm-hmm.
Also, on the syllabus, it just says like the week that the first exam.
Yeah, I don't know for sure yet what the day. Isn't it not next week, but the week after? Isn't that what I scheduled it for? Yeah, so sometime that next week. I'm thinking probably either Monday or Wednesday of that next week, but I'm not positive. So let me show you can program Mathematica to figure this out for you. You can do modular arithmetic in Mathematica. You can mod any number, say 7, by any other number, say 3. What's 7 mod 3? It's 1. What's 8 mod 3? It's 2. What's 9 mod 3? 0. So you can do modular arithmetic in Mathematica. And if you want to, if you had one of these U groups and it was a really big one, say order 32 or something, and you're wanting to figure out the orders of elements quickly, well, there's a few different things that you could do. You could, like if you were thinking one element at a time, you could use the table command that creates lists. You could take your particular element, like say we take the element 3 here, and keep multiplying it by different values of I, or excuse me, I should raise it to powers of I, excuse me. Mod it by 16, and let I range from, conceivably it could have been cyclic, so I'd going to probably at least go from 1 to 8. So here's 3 to the first power, here's 3 squared, 3 cubed is 27, mod 16 is 11, 3 to the 4th is back to 1 like we saw. 3 to the 5th would be 3. 3 to the 6th would be 9. 3 to the 7th would be 11. It's cycling. That's why these things are called cyclic groups. 3 to the 8th would be back to 1. Yeah, say we're thinking about U64. Oh, here's another thing you could do. What if you want to do? Well, U64 would be relatively easy to figure out the elements of it. It would be all the odd numbers from 1 to 63, because 64 is power of 2. What if you're thinking about, say, U60, and you're trying to figure out what the elements of U60 are with Mathematica quickly? You want the positive integers less than 60 that are relatively prime to 60. Coprime, I think it is. Coprime? No. Prime. What was coprime? There it is. CoprimeQ is a Mathematica function that will tell you whether two given numbers are relatively prime or not. So for example, 4 and 9 are relatively prime. This should return true. 4 and 10 are not relatively prime. This should return false. So I could combine that with the table command. I could go table coprime. If I'm thinking about U60, what numbers n, say, less than 60, positive integers n, are relatively prime to 60? Let n go from 1 to 59. Get a bunch of trues and falses. Maybe that's not so helpful because you don't see what number they're going with. If we also made a list in here telling you what n was each time. Every time you see a true, that's then an element of U60, like 31, 37, those are also prime numbers. See, where's an example, one that's not prime, that's in U60? I don't see any examples. And 60 is what? 3 times 4 times 5. 49 is an example. There we go. Yes. 7 is an example. Actually, if you put this in table form, it'll look nicer. There we go. So that would quickly give you the elements of U60, and then you could search for generators to see if U60 is cyclic or not. And I bet I could probably write a little program that would test for generators or something fairly quickly. But this is more basic stuff. So I would encourage you to experiment with this kind of stuff and use it. I will go ahead and save this and put it on Moodle for you, and you can play with it if you like. Okay, so U16 is not cyclic. There's your exploration for the day. Let's spend some time thinking about the proof that you turned in today. Next. I gave you a hint on Moodle. So the problem was, suppose G is a finite group with order equal to, say, some number n, some positive integer n. And suppose H is a subgroup of n, or a subgroup of G. I'm now looking at the problem statement in the book. I'm trying to remember it and paraphrase it, so to speak. I'm not trying to get it word for word, which reminded me when I was thinking about that, as I wrote this down, for the exams, I did tell you, when you do write definitions and theorem statements down, it doesn't have to be word for word. And so you don't literally have to spend time really focusing on memorizing definitions and theorem statements word for word. However, I mean, it doesn't hurt to memorize them. The important thing is that you understand them. They're going to stick in your mind better, and you're going to understand what they say better if you focus more on understanding them and maybe recreating a definition from scratch, even if you forgot it or something, just by your understanding stuff. And again, I'm not looking for word restatements. I'm looking for correct meaning. So I'm essentially paraphrasing this problem based on my recall, and sure, I'm not stating it the exact same way. What was the goal? The goal is to prove that the order of h cannot equal n minus 1. And n does need to be bigger than 2 here. Because if G had order 2, then H could be just the identity. So I'm not going to write a polished proof right away. In fact, I won't write a proof at all, but let's just think through the problem-solving process based on the hints I gave you. This, when you're trying to show something is not true, is another good candidate for a proof by contradiction. When you're trying to show something is not true, which, by the way, does apply to things like showing square root of 2 is irrational, which I think I might have done in the lecture, if I recall correctly. One of the lectures. I don't remember for sure if I did it. Showing square root of 2 is irrational means show it's not rational. That's what irrational means, not rational. That's a good candidate for a proof by contradiction. So assume to the contrary that it is rational. Here we're trying to prove the order of h is not some number. That's a good candidate for a proof by contradiction. So scratch work or proof. This is not a proof. Suppose the contrary, that the order of h is n minus 1. If it's helpful, you could draw a Venn diagram or a couple blobs here. Say G has order n. H takes up almost all of G, so to speak. The order of H is n minus 1, or maybe I'd want to draw that even differently, and maybe I'd want to include part of the boundary or something. To emphasize that there's just one element that's in G but not in H. All this would imply there exists a unique, that's not exists factorial. Backwards Z means there exists, and if you put an exclamation point next to it, it means there exists unique. That's standard shorthand. Unique element, call it A, in G but not in H. You could write that as a set difference, G minus H. That means in G but not in H. Some people write it like this as well. Okay, great. So there's a unique element in G but not in H. That uniqueness must be important for this proof, perhaps. I mean, if this was an n minus 2 instead of n minus 1, then we'd have 2 elements. I mean, maybe it's possible the order of H can't be n minus 2 either. And in fact, that's actually true. If n is greater than 3, at least. No, that's not quite true. N would have to be greater than 4. Because if n were 4, subgroups of order 4 can have, groups of order 4 can have a subgroup of order 2. So n would have to be bigger than 4 in that case. How might this be relevant to the proof? Do you remember what you did? So n is at least 3. There's at least 2 elements in H. At least one of which, or exactly one of which, would have to be what? Our favorite element? The identity. So here's there's A. The identity's got to be in H. It's a subgroup. And there's got to be at least one more element in H. I don't know, call it B. N being bigger than 2 implies not that there exists a unique element, but exists at least one more element. At least one B in H with B not equal to the identity. And since B is an H and A is not an H, B also does not equal A. I think I gave you a little bit more of a hint after this point. Do you remember what I said? I think I said this to explore what happens when you multiply A times B. And what can you say and how do you get a contradiction out of that? What is A times B? Well, you don't know what it is, but there's two elements you can definitely say it's not. What two elements can you definitely say A times B is not? A and B, or did you say E and B?
I said E.
Okay. It's actually A and B. It could equal E. And it could also equal some other element that I haven't listed here, C, that would have to be an H because it's not equal to A. Yeah, you don't know for sure what it is, but it can't be A and it can't be B. Because if it were A, if A times B were A, that would imply by cancellation that B is E. That's a contradiction because B is not E. It's not my overall contradiction proof, but it's a contradiction to the assumption that A times B equals A. And it can't be B because if it were B, then A would equal E, and A is not E as well because A is not even an H. So it could equal E, maybe, or it could be if N is bigger than 3 at least, there would be some other element. And we're not saying what N is other than it's bigger than 2. It's good enough just to say there's some other element, C, which could be E, but there exists an element C in H. It's got to be an H because A is the only element that's not an H, such that A, B equals C. I claim we're almost done. That's almost clearly a contradiction. Why is that almost clearly a contradiction? Almost clearly, does that make sense? Well, it's fairly quick and clear, but there is sort of one step you should say here to get the final contradiction. What should you do with this equation to most clearly see that this is a contradiction? Should I solve it for maybe A or B? And if so, which one?
Solve it for A.
Solve it for A. Which means, at least in this form, writing it as A times B, I don't want to write and multiply by B inverse. Yeah, why is that pretty clearly now a contradiction? It implies A is an H by closure of H. Since H is a subgroup of G and B and C are in H, and therefore B inverse is also in H, closure. And that is a contradiction because we assumed A was not in H. When you reach a contradiction, some mathematicians like to put this kind of symbol near the end when you got your contradiction. I like to draw it like this. Now, sometimes you'll see it more like this. But when my math teachers did that kind of thing for a contradiction, I always thought, oh, that's a star. But no, it's not a star. It's two arrows pointing at each other. So drawing it a little bit more like that makes it more clear that it looks like two arrows pointing at each other. They're contradicting each other, is the idea of that picture. That's a contradiction. You can highlight it with these two arrows pointing at each other. You should say at least one more sentence. Therefore, our original assumption that the order of H was n-1 must be false. So the order of H can't be n-1. Could I see putting a proof like this on the test? I think it's possible. It's not super hard. It's not super easy either. It's the kind of thing that does take a little bit of creativity, you might say. And so that does make it maybe a more difficult test problem. Takes some scratch work, takes some exploring, which does need to take some time. If it were a test question, it would be, you might say, one of the harder ones because of that possibility. Mm-hmm.
How do we know that C is in
Because C can't equal A. A times B can't be A, because it would imply B equals E.
A times B in H?
Because it can't equal A, and A is the only element that's not an H. It's the fact that we were assuming the order of H was n-1 that is part of that.
Okay.
A is the only element not in H. Therefore, since A times B can't equal A, it's got to be equal to something in H. C could be the identity, but it might not be. Good question. Maybe just like on the homework, if I put something like this on the test or something of equivalent difficulty, I'd give you a little hint to get you going. All right, I think it'd be good to spend some time looking at the reading and emphasizing the kinds of things you should do when you do the reading. In particular, chapter 4. Chapter 4, I do feel like on the first read through seems more difficult than chapters 0 through 3. I mean, chapter 0 felt difficult and long too. But actually now you should be at the point where you look back at chapter 0 and say, oh, chapter 0 is actually not as bad as it felt at first, if you look back at it. But chapter 4 feels challenging, I think, on a first read through. There's a lot of things here, for one thing. And I guess what I'd like to do is just sort of recommend that when you read theorems, yeah, reading their proofs is great and trying to understand their proofs is great. And this one's not super hard. It involves using the division algorithm. You should think about both the overall strategy and the details. But also think about examples. And don't just read the book's examples, come up with your own examples. I think theorem 4.2 is a good one to think about here. because that one looks pretty confusing when you first read it. Let A be an element of order n in a group. Not saying whether the group itself is finite or infinite, just saying this element has finite order. We did see maybe a week ago, there's at least one group, actually more, there's at least one group that's an infinite group that's got finite subgroups that are not just the identity. Yeah, we saw a few examples of that. One prominent example is the complex numbers. Has plenty of finite subgroups consisting of elements on the unit circle. You remember that? The operation was multiplication, by the way. Complex numbers take away 0, I should say. I called it C star under multiplication. Then you can say that the cyclic subgroup generated by a to the k is the same as the cyclic subgroup generated by the GCD of n and k, or a to the GCD of n and k power. And moreover, you can say the order of a to the k is n divided by the GCD of n and k. That's hard to wrap your mind around without thinking about examples. And yeah, the book's got examples, but make up your own. Suppose, take an example, relatively small order, maybe order 12 or something. Or we thought about Z12 the other day. Let's pick a different one. Order 20. So suppose the order of A is 20, which is 4 times 5, 2 squared times 5. It's going to turn out as we continue going through the book that knowing the prime factorization of n will be often handy, especially when we get to chapter 8, I believe it is. Then we'll start really using prime factorizations a lot. What is, for example, or what are, I should say, the order of a squared, the order of a to the 3rd power, order of a to the 4th, order of a to the 5th, and I could keep going. Maybe that'll be good enough. At first attempt at this without looking at the theorem, you should just attempt to do the calculation. A squared squared is a to the 4th, which is not yet the identity since the order of a is 20. A squared cubed is a to the 6th, etc. The first time you're going to get back to the identity is when it simplifies to a to the 20th, which will happen when you raise a squared to the 10th power. That's the first power of a squared, first positive power that will get you back to the identity since a has order 20. Therefore, the order of a squared is 10. Okay, does it match what this theorem says? We just figured out the order of a squared, k is 2. What's the GCD of 20 and 2? That's 2. N divided by the GCD of n and k here is 20 divided by the GCD of 20 and 2. 20 divided by 2 is 10. Yay, they match. Let's skip a cubed for the moment. That one's a little bit harder because it takes more writing, you might say. Let's go to a to the 4th. A to the 4th squared is a to the 8th, not the identity. a to the 4th cubed is a to the 12th. A to the 4th to the 4th is a to the 16th. A to the 4th to the 5th is the first time you get to the identity. Therefore, the order of a to the 4th is 5. What's 20 divided by the GCD of 20 and 5? That would be 20. I meant 4. K is 4, excuse me. 20 and 4. That would be 20 divided by 4 is 5. It's easy to get mixed up. I almost wrote a 5 there instead of a 4. But K here is 4 because it's the power of A that we're thinking about. Yeah, and a to the 5th is going to have order 4. The first positive power of a to the 5th that gets you back to the identity is the 4th power. The order of a to the 5th is 4. And 20 divided by the GCD of 20 and 5, K is 5 because I'm thinking about a to the 5th, is 20 divided by 5 is 4. They match. So when you think about examples like that, that helps you believe the theorem and understand the theorem better. What about this part of it? Why is the cyclic subgroup generated by a to the 4th, for example, when K is 4? Why is it the same as the, well, okay, the 4 is, that's an easy case. GCD of 20 and 4 would be 4. More interesting, if K were 12, yeah, and that's a more interesting thing to think about initially here. What is, we were thinking, except when we skipped 3, we were thinking about divisors of 20. What is the order of a to the 12th? Okay, before we use the theorem or compare to the theorem, let's go ahead and do the calculations. A to the 12th squared is a to the 24th, which, since a has order 20, you'd want to think of as a to the 4th times a to the 20th. A to the 4th times e is a to the 4th. It's cycled back to a to the 4th. Now the identity. A to the 12th cubed is going to be a to the 36th. Think of that as a to the 16th times a to the 20th. A to the 16th times e. So a to the 16th is not back to the identity. A to the 12th to the 4th power, a to the 48th. Think of that as a to the 8th times a to the 40th, which is a to the 20th squared. A to the 8th times e squared is a to the 8th times e is a to the 8th. You don't have to show quite so many steps, but just to be explicit, this is not yet the identity. A to the 12th to the 5th is a to the 60th. 60 is a multiple of 20. That's a to the 20th cubed. E cubed is e. Looks like the order of a to the 12th is 5. Yeah, this is more significant. Does this match the theorem? What is 20 divided by the GCD of 20 and 12? Sorry, I keep thinking I'm still on the camera here. The GCD of 20 and 12 is 4. Not equal to K like it was for the other examples. Smaller than K, but this is 5, still confirming the theorem. And yeah, this part is saying the cyclic subgroup generated by a to the 12th would be the same as the cyclic subgroup generated by a to the 4th. we have essentially done the calculations to find the cyclic subgroup generated by 8 to the 12th, including E, which is 8 to the 0 power. It's E, 8 to the 12th, 8 to the 4th, 8 to the 16th, 8 to the 8th, and then back to E, which we already included. And yes, those are all powers of 8 to the 4th as well. This is the same as the cyclic subgroup generated by 8 to the 4th. And I hope you remember, when you write sets, you don't have to write things in the natural order. The order doesn't matter. So it doesn't matter that I'm jumping around here with these powers. The set is still the same. Got the same elements. So yeah, maybe even instead of looking at the book's examples, make up your own examples. Of course, it's not bad to look at the book's examples, but doing so is maybe not as good, especially if you're just reading them and not checking the calculations yourself. Maybe it's not as good as making up your own examples. Let's look at the theorems about the Euler Phi function as well here. I haven't mentioned the Euler Phi function, I think, in class. Euler Phi function here. They're trying to get to this theorem. The number of elements of each order in a cyclic group, if D is a positive divisor of n, then the number of elements of order D in a cyclic group of order n is phi of D, or phi of D if you prefer. Or this is the Euler Phi function, or Euler Phi function if you prefer. Is it phi or phi or pho or phum? It's phi or phi, either way is okay. I double checked with the Greek professor. He said, yeah, phi or phi, either way is okay. You know, fraternities say phi. Physicists should typically say phi. Mathematicians seem to always say phi. So I'm a mathematician. I got used to that. I always say phi. It just, I don't know, it just seems to be a pattern. Not always true, probably, but seems to be what I always noticed. So the Euler Phi function is defined, first of all, to be phi of 1 to be 1. And for any integer n greater than 1, phi of n is the number of positive integers less than n relatively prime to n. Hey, by definition, phi of n would be the order of un, because un is the positive integers less than n that are relatively prime to n as a set. So whatever this phi of n is, in general, it does always equal the order of un. And here's some values of phi n that you can check. Notice that for any prime number like 7, phi of that prime is 1 less than the prime, 6 in that case. Phi of 5 is 4, phi of 11 is 10. That should make sense. If n is prime, they're going to be n minus 1 positive integers less than n that are relatively prime to n, if n is prime. For non-primes, I mean, you can check all those numbers, but it's not so clear perhaps why they equal what they equal. You know, what's the deep reason for it? It is evidently, if you go on the next page, based on the fact that you actually can find the values of phi of n using an algorithm, you might say. If you plug in a power of a prime, p to the n, then phi of p to the n is p to the n minus p to the n minus 1, and that's not too hard to see. If you got a product of two relatively prime numbers, m and n, this is true. That's maybe a little less clear. And based on this, you can use prime factorizations to figure out phi of any number. Like, what if we wanted to know phi of 60? Write 60 in terms of its prime factorization. It's 5 times 12, which is 2 squared times 3 times 5. This property here extends to the product of more than 2 relatively prime numbers. You can do that by induction to prove that. 2 squared, 3, and 5 are all relatively prime. So this is the same as phi of 2 squared times phi of 3 times phi of 5. Phi of 3 is 2, phi of 5 is 4, because those are prime numbers. Phi of 2 squared, 2 is a prime, and so 2 squared is a power of a prime, according to this formula, is going to be 2 squared minus 2 to the first. 4 minus 2 is 2. Yeah, 1 and 3 are relatively prime to 4. This is 16. Therefore, the order of U60 is 16. Did we see 16 truths when we used Mathematica? Let's count them. I could also, there's a Mathematica command that would count them as well. 1, 2, 3, 4, 5, 6. I'm at 19 there. My 6th true. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. 16 truths in that list, corresponding to the elements of U60. Mathematica can compute the Euler Phi function as well. I think it's Euler Phi, yeah. Euler Phi of 60, 16. Capital E, capital P. And coming back to the book, in these theorems, what do they say? Think about what they say here. If D is a divisor of n, the number of elements of order D in a cyclic group of order n is phi of D. So say you're talking about a cyclic group of order 60, for example. That would be, for example, Z60 under addition. Well, the number of generators is going to be phi of 60. It's going to have 16 generators. Does that make sense? If I take both D and N to be 60, 60 divides 60. I'm thinking about Z16. It's going to have phi of 60 generators, 16 generators. In fact, the generators of Z60 under addition are going to be the same as the elements of U60 under multiplication. 49, for example, will be a generator of Z60. Z60 has 60 elements. 49 will be a generator of Z60 under addition. That's not so obvious if you didn't know these theorems. Could we confirm that with Mathematica? We could, yeah, we could use table and we could look at the multiples of 49. 49 times I, not 49 to the ith power, because I'm thinking about Z60 here, which is addition. It's not going to be until I get to I equals 60 that I'm going to get a 0. 0 being the additive identity of Z60. I forgot to mod. Mod by 60. Yeah, only in the very last spot do you get a 0. 49 is a generator of Z60 under addition. It's also one of the elements of U60 under multiplication. Z60 has 60 elements and 16 generators. U60 has 16 elements. Is U60 cyclic? Did we answer that question? I don't know offhand. I'm guessing not, but I might be wrong. If I'm right that it's not cyclic, then 49 would not be a generator of U60. It's an element of U60, but not necessarily a generator. Because I think probably U60 is not cyclic, but I need to think about that. There's facts in chapter 8 that allow us to say whether U60 is cyclic or not. If D is something other than 60, say we're still thinking about Z60 here, N is 60, and D is something other than 60, but still divides N, like 15, then the number of elements of order 15 in Z60 would be phi of 15, which I think is 8. Yeah, it's phi of 3 times phi of 5, which is 2 times 4 is 8. There would be 8 elements of order 15 in Z60. There's actually nothing special about Z60. 15 also divides 150. There'd still be phi of 15, 8 elements of order 15 in Z150 under addition mod 150. The answer only depends on what D is, not what N is, as long as D divides N. And that's something the book emphasizes down here. Z8, Z640, Z80,000 each have 4 elements of order 8. They're different elements. In Z8, the elements of order 8 would be its generators 1, 3, 5, and 7. In Z640, the elements of order 8, can you think with me here, would include 80 for 1, right? 80 would have order 8 in Z640. Also 3 times 80, 240 would have order 8. 5 times 80, 400 would have order 8. And 7 times 80, 560 would have order 8. Does that make sense? Okay that I'm not writing it down? Maybe you want to write that down? Those things down? 80 definitely has order 8. And yeah, multiply it by 3, 5, and 7, you're going to get the other 3 elements of order 8. Analogous to the fact that the elements of order 8 there are 1, 3, 5, and 7. Well, multiply 1 by 3, 5, and 7. Here in this one, 80,000, 10,000 will have order 8. Also 30,000, 50,000, and 70,000. Those will be the only elements of order 8. Corollary is in a finite group, the number of elements of order D is a multiple of phi of D. Doesn't say anything about the group being cyclic there. In the theorem, the group was cyclic. Here's just a finite group. So in finite groups that are not cyclic, you could have more than phi of D elements of order D, but it's got to be a multiple of that. That's maybe less intuitive why that's true, but they do give a proof here. Take an example. Hope you believe this. Well, let's think about how about D4. Let's say the group is D4. D4 symmetries of a square. dihedral group of order 8. It's got 8 elements. It's got 4 rotations and 4 reflections. That's the one that has the Cayley table in the book. You might wonder, how many elements of order 2 does it have? It's got to be a multiple of phi of 2. Phi of 2 is 1, so that's pretty trivial. But it does have more than one element of order 2. It's got 5 elements of order 2, actually. No. Yeah, excuse me, it does. Okay. There's D8. 5 elements of order 2 include all the flips, all 4 flips, reflections, H, V, D, and D prime. Also, R180 has order 2. It's got 5 elements of order 2. Phi of 2 is 1. 5 is a multiple of 1. Of course, any positive integer is a multiple of 1. So the theorem is not really saying much there, but it is confirming that it's true. Notice the number of elements of order 2 doesn't have to divide 8 here. Doesn't have to divide the order of the group. How many elements of order 4 does it have? Have to be a multiple of phi of 4. Phi of 4 is 2. Actually, it does have just 2 elements of order 4. R90 and R270 would have order 4. There we are matching phi of 4. So again, thinking about not just proofs, but examples is really key. All right, we've got a few minutes here more. Let's go back to just starting to think more about groups of permutations. And well, since we're low on time, maybe I should just define what a group of permutations is. This definition is the first definition in chapter 5. A permutation group on a set, I think the book calls the set capital A. That's a set capital A, that's the word A, right? A permutation group on a set capital A. Maybe I should do this. Is any collection of one-to-one and onto functions from A to itself. I'll draw the arrow, but I won't bother drawing function names, which forms a group under what operation? Under function composition. The elements of any permutation group are always functions that are one-to-one and onto from a set to itself. Nothing about A necessarily being finite. Most of the examples we consider, A will be finite, but A could be infinite. In fact, this point of view of permutation groups allows us to realize that actual geometric rotations and reflections can be thought of as permutations. You do a rotation by, say, 90 degrees, you can either think of that as rotating the entire plane by 90 degrees around some origin, or you could focus on a particular shape and the points in that shape. say a square, the A, in the case of the plane, would be the entire plane. If it were just focusing on the square, it would be all the points in the square. Those are infinite sets. A would be infinite there. But such functions, like a rotation by 90 degrees, are necessarily one-to-one and onto. Reflections are also one-to-one and onto. And yeah, say you think about D4, for example, symmetries of square, that would be a set of 8 functions that could be thought of as permutations under this definition that do form a group under function composition that could be thought of as a permutation group. So this definition allows for that kind of example as well. But our main example in chapter 5 is got a special symbol, S sub n, and has a special name, the symmetric group on n objects. That really can be any n objects. Could even be people, for example, set of people. But typically, in this case, we think of A as being what I've called Cn before, but again, that notation Cn is not standard. We typically take it to be the first n positive integers. But you're not, just realize, as I've emphasized, you're not multiplying or adding those numbers. You're just thinking of those as objects that are being permuted, reordered, you might say. Permutations on finite sets reorder the elements, so to speak. And that's most clear in the array notation rather than the cycle notation, that you're reordering things. That's how it's related also to probability and statistics. It's a reordering of finitely many elements. Okay. Chapter 5 definitely is a chapter where, as you read, you want to think about examples and make up your own examples as you go, because it's hard, just like chapter 4 is. Okay. Have a good day.